So, good evening, everyone. Let's get started with today's interactive session. Welcome. So, I'm your TA for the interactive session on fluid and particle mechanics offered on NPTEL. This course is offered by Professor Sumesh and Professor Basavaraj of Chemical Engineering Department in IIT Madras. I am Shankar. I'll be your TA for your weekly sessions. Usually these classes will be held on Mondays from 6 o'clock to 8 o'clock, but since I'm traveling for this and the previous week or the previous week, we've been having this at another time that is more suitable for me. I do apologize for that. So let's get started with the classes. Yeah, so last week we were doing this question on Bernoulli's equation, where so this is again part of week 2 problem. We have not started with week 3. So let's just go through what's given here. Let's try to attempt from what's given the question, and then the next part we'll move on to the next week's lecture. It's given that air at 110 kilopascal and 50 degrees Celsius flows upward through a 6 centimeter inclined duct at a rate of 45 liters per second. The duct diameter is then reduced to 4 centimeter through a reducer. The pressure change across the reducer is measured by a water manometer. The elevation difference between the 2 points on the pipe, that means from here to here, is 0.2 millimeter. Determine the differential height between the fluid levels of the 2 arms of the manometer. That means this h is what we need to find out. So let's start with Bernoulli's equation. I'll be typing out the equation because that's more comfortable, I feel. I'm not able to write it because my iPad is currently under repair. Moving on, so we'll start with the Bernoulli's equation, which is given by P1 by, let me just insert the symbol for rho, the density, P1 by rho g plus, it's P1 square by 2g plus h1 is equal to the same on the other side, P2 by rho g plus P2 square by 2g plus h2. Yeah. So this is the Bernoulli's equation for flow, the energy balance for a flow past flow through a body or flow between 2 points. Now let's make use of this and Bernoulli's equation to find out what these terms are. First it is given that air is at 110 kilopascal and it goes from P1 to P2 over here. But we need to understand that since it's flowing through this one, there is a change in the pressure as well as change in the flow rate. So let us first calculate what is B1 and B2. And it is given that Q is 45 or Q is flow rate in of the air in liter per second. It's 45 liter per second, which would be equal to 0.045 meter cube per second. Oh, sorry. Now we can find V1. Yeah, we can find V1 by just dividing the Q with the area. That's equal to, again, yeah, pi d raised to d square, or it will be 4q by pi d square. If it's diameter, then you have to divide it by the, make it into radius. And this should be equal to V1. So we'll get V1 as 4 times 4 times 0.045 by pi times d square, and V1 will be the velocity at this inlet, and the diameter of the pipe at that point is 6 centimeter, so it will be 0.06 square. Yeah. Similarly, V2 will be the very similar to this. Here it's the only difference is that there is one, it's pi d1 square, which is given by here, and V2 will be pi d2 square. And it will be here 0.04. That is 4 centimeters as shown here. Yeah, we have V1 and V2. We need to find out basically the pressure difference given by P1 by rho g minus P2 by rho g. And from that we can find P is equal to, we equate that to P equal to rho g h, and thereby find the value for h. Now what we need to understand is rho that is given here is in fact the density of the fluid that is moving inside the tube, which is in fact the air, and not the one that is inside the manometric limb. Similarly, here as well, we need to understand that the density of the fluid in the that's being flown is being considered in these equations, and not the manometric fluid. If you don't have the manometric fluid also, we'll still get the same equation. So basically this is what needs to be understood from the definition. So we have V1, we have V2, we have rho air. We can assume rho air to be equal to, almost equal to 1, or we can just take it as 1.05 kilogram per meter cube. This would be the density of air in that. Yeah. So we have the density of air, we have V1, V2, and we just need to find out H1 and H2. So we know that the elevation difference between the 2 points where the arms of the manometers attached are is 0.2. So if this is considered as the datum, so if this is considered as the datum, let me just make this a little bit larger, make it a little bit dotted. Yeah, if this is considered as the datum, then this height from the datum to that point will be 0.2 meters as given here. So yeah, this height is actually 0.2 meters. Yeah. So therefore, if we consider h1 to be 0, then h2 will be 0.2. So h1 should be equal to 0 and h2 to be equal to 0.2 meters. So we have all the equations, we just need to substitute and find what the P1 minus P2 by rho g is. We know that if the flow is happening in this direction, the pressure here has to be higher than the pressure over here, only then flow will happen in this direction. Therefore, P1 minus P2 can be evaluated from the above equation by just rearranging the terms over there, and we'll get a value. Oh, we can actually find out what is P1 by rho ARG and P2, P1 minus P2 by rho ARG over here, just by rearranging this. And from here, what we need to find out is actually the difference in the pressure by denoted by delta P, which is P1 minus P2, and you'll get that value over there, and you have to equate that change in pressure of air in the two columns to the change in the manometric fluid, the change in height of the manometric fluid. But what you need to consider here is not actually the row of air, and you need to actually consider the, since it's given that it is a water manometer, you have to consider row of water times H to be the change in pressure over here. And from here, the delta P will get from the above equation, and from here you will be have to equate that over here, and from that you will get the final value for H, and here H is the difference in the column height. All these are just very straightforward calculations. I'll wait for a couple of minutes and then give out the answer. So you'll get V1 as 15.92 meter per second. You'll get V2 as 35.81 meter per second. What you need to understand is that since the diameter at the second location is smaller, the velocity will be much higher than that at V1. Then you'll get delta P as, just let me complete the calculations. I'm doing it side by side. You'll get it as around 52.66 meter here, because the unit that's given in this equation is in meters. Therefore, you'll get delta P as roughly equal to 542.4, and you'll get the height as 5.52 centimeters. Okay. Yeah, please let me know if there are any questions. If you have any doubts, this will be in actually Pascal. Sorry, this will be in Pascal. Let me know if you have any doubts in this question. So the answer is very straightforward, or the method of solution is very straightforward over here. You have air flowing through a duct like this, inclined duct like this. You don't have to worry about the inclination angle and all right now. Now all you need to do worry about is the vertical distance between the 2 points that are being considered. And yeah, so this is a simple solution of the Bernoulli's equation that's given over here. We have all the details like Q and velocity, and we have V1 and V2. We have the density of air, the H1 and H2. We have delta P or P1 minus P2 by rho G as 52.66. We have delta P as rho water times G times H as 542.4, and finally we get the height as follows, as 5.52 centimeters here. Okay, let's move on to the next question. And before we move on to week 3's questions and problems related to week 3, we will first deal with what is there in week 1. So in week 1, we've been assigned multiple questions, assignment questions, which are in fact graded, and there was an assignment session which was not graded. We will discuss both of them after the last date has been announced. Now in here, if you take a look at this, I think, yeah, if you go to Swayam website, if I sign in using my account, recording in my system, so let me just start again. We'll be dealing with the questions related to week 1 assignments. And in the first question, we have a fluid at 20 degree, water at 20 degrees Celsius, which has a viscosity of 1 centipoise. The width between the two plates is 11 millimeter or 0.011 meters. We need to find out the shear stress that is required to move the plate at a certain velocity. So we have a moving plate that is at 5.5 meter per second, and we have a fixed bed plate, and there is a gradient in the velocity which is linear. Therefore, it is just a direct application of Newton's law of viscosity, where the shear stress is given by tau, that is equal to mu times du by dy. Mu times du by dy, and it's given that the viscosity of water is, it's not given, you have to understand that viscosity of water is 0.001 Pascal second or kilogram per meter second, or whatever unit is in SI units. Next, yeah, so we know that since it is linear, we can take du by dy to be equal to delta u by delta y. Since it is in the linear regime, we can just directly take this assumption. And we need to understand that the top plate, which is moving at a velocity of 5.5 meters per second, and the bottom plate is actually stationary, and the top plate is at a distance of 11 millimeters. So yeah, get 0.011 minus 0, and we'll get a value for du by dy from here. In fact, we'll get that value to be around 500. And therefore we can directly find out what tau it is from this equation directly, which is given by mu times du by dy, which is 500, which is equal to 0.5. Yeah, so yeah, that is the correct answer over here as shown in the question. Now for the second part of the question, we have been asked to find out what the Reynolds number is if the characteristic length L is to be taken as the distance between the plates. So we know that Reynolds number has the formula rho times u times d divided by mu, and all we need to substitute is the other values for rho for water, which is approximately 1000. U is the velocity 5.5 times the characteristic length, that is 0.011, divided by the viscosity 0.001. You will get this answer to be as 60,500 if I am not wrong. Yeah. Okay, moving on to the next question. We have a question on manometers, which is given as this. Consider the three liquid system in figure 2. Neglect air density. If H1 is given as 6 centimeter, what will be the density of the fluid marked as water? So we need to find out what this density of water is, and if H1 is 6 centimeter. And we know that mercury, we need to understand that the density of mercury is 13,600 kilogram per meter cube. And we need to find out what the density of water and reverse calculate it actually. So as we have done for the questions for manometers in the first week itself, it will be very straightforward for us. We know that when you have to go down, we need to understand that these are three manometers that are in parallel, which means they have a common connection here. Therefore, the pressure of each of them will be the same. That means total pressure in this column should be equal to the total pressure in this column, which is again equal to the total pressure in this column. It's not like you have to add these two to this or this becomes 2 into this. All the pressure in each limb will be the same, and we can equate that and find out the value of the density of water for the first part and the value of H2 H2 for the second part. So we know that if we have mercury over here which has 8 centimeter and mercury here which is almost 6 centimeter, the differential height between these two limbs for mercury will be in fact 2 centimeter. So we can just equate that part. P water should be equal to the differential height in mercury, and we know that the pressure of water will be 1000 times 9.81 times the height, which is in fact 27 centimeter, which is 0.27 meter. Sorry, we need to find this term. Sorry about that. We need to find this term over here, that is the density of water. And we need to equate this to the pressure of mercury, and that is not equal to 8 centimeter because mercury also has 6 centimeter here. It will in fact be the differential pressure. That means this is 6, this is 8, therefore there is a 2 centimeter difference. So 13,600 times 9.81 times, it will be 0.02 since the height in that pressure is height in the column is 2 centimeter. Finally, we get the density of water to be equal to, just by resubstitution, we can just do a calculation over here. we'll get this value as 1007.41 kilogram per meter cube. Yeah, this is for the first part, and for the second part we need to find out what H2 is. That is, H2 is the height of oil in this limb, which is given, the specific gravity of the oil is given as 0.78, and we know that the specific gravity is the density of oil to the density of water at that particular temperature. Therefore, we can find out the density of oil to be equal to 780, which is basically, or let's just say 0.78 times the density of water we just found out, which is 1007.4. which is equal to 785.77. Yeah. So now we consider the pressure balance, hydrostatic pressure balance, the mercury in the second limb to the overall fluid in the third limb. And we know that the pressure balance will again follow the same formula as rho mercury times G times the height of mercury in the differential height of mercury should be equal to the density of oil times G times height of oil. And mercury's density is again 13,600 times 9.81 times the height of mercury refers to the differential height. This is 8 centimeter, this is 5 centimeter. Therefore, the differential height will be 3 centimeter. So times 0.03 should be equal to the density of oil we just found out is 785.77 times 9.81 times the height of oil is what we need to find out, and is I think marked as H2 over here, as you can see. And yeah, from here it is very straightforward calculations where we need to find out H2, and this value, I think if we just do a calculation here, will be coming out to around 51.9 centimeter. Yeah, 52 centimeter roughly. Anywhere in the range of 50 to 55 is acceptable for our purpose. Okay, if you have any questions, I'll just wait for a couple of minutes for you to catch up, and I'll ask. If you have any doubts, please let me know. Okay, let's move on to question number 3, where it's given that 3 pipes steadily deliver water at 20 degrees Celsius to a large exit pipe as shown in figure 3. The velocity V1 is 5 meter per second. The exit flow rate Q4 is 120 meter cube per hour, and it is known that the flow rate in pipes 2 and 3 are the same. Actually, I just may have forgot to add the statement. Yeah, find the velocities in pipes 2, 3 and 4, and D1, D2, D3 and D4 is given. So we know that the velocity in V1 is 5 meter per second. Therefore, we can find the flow rate here, and we know the Q4 is 120 meter cube per hour, and we can find the value in meter per second over here. We can find the flow rate in Q2 and Q3 since it is given that the flow rate in pipes 2 and 3 are the same. We can find the flow rate in each of these pipes, and thereby we can directly find the velocities in pipes 2, 3 and 4. So let's just quickly try to complete the question. We know that flow rate is velocity times the area. So based on that, let's find out what the value of Q1 is. And the area is given by pi d square. And we know that V1 is 5 meter per second. And D1 is 4 centimeters. So we'll get Q1 from here in meter cube per second. And this value, let me just do the calculations quickly. Yeah, it will come to 0.025 meter cube per second. We know what is Q4, or sorry, Q4, and that is given as 120 meter cube per hour, which is in meter per second will be 120 by 3600, which is 0.033 meter cube per second. Therefore, we know that Q2 and Q3 are equal. Therefore, if we just take mass balance across this, we know that Q1 plus Q2 plus Q3 should be equal to Q4. If we are equating Q2 and Q3 and just calling it as Q, we can just write it as Q1 plus 2 times Q should be equal to Q4. Therefore, Q will be equal to Q4 minus Q1 by 2. And that will be coming out to 0.004 meter cube per second. Now that we know Q2 and Q3, we can directly find the velocity in each pipe. Therefore, V2 should be equal to Q 2 divided by, again, should be pi d2 square by 4. Oh, oh, sorry, I think I made a small mistake. There is 1 by 4 times pi d square. So this value has to be multiplied with 0.25, and you'll get the value as 0.00625. And you'll get this value as 0.0267 meter cube per second. Oh, sorry, 1 second. 0.033 minus 0.00625 divided by 2. It will be, in fact, 0.0133 meter cube per second. Therefore, V2, you just have to substitute the value of, excuse me, Q2, just 0.0133 divided by 4 times this value by, again, V. I think, yeah, Q2 has a diameter of 5. Therefore, you'll get V2 from here. Similarly, V3 and V4 can also be found in some similar manner. And we know that D2 is 5, D3 is 6, and D4 is 9. Both will be 5, 6, and 9, and we'll get the velocities over here. Now we just need to calculate this, so I'll give a couple of minutes for calculation. You'll get it as 5.24 meter per second over here. Nice. Yeah, there'll be some small variations because the numbers are associated with this, but otherwise it will be more or less the same. Yeah, you'll get 5.19 as per this calculation in my phone. So you have all the velocities here, you have all the flow rates here. Yeah, that velocities is what is asked in 2, 3, 4. So I'll wait a couple of minutes. If you have any questions, please let me know. Okay, we'll move on to the next question. In the question, it is given that given the steady incompressible velocity distribution u, a, v, and w as by square, ax square, and c x square y square, a, b, c are constants. This flow satisfies the equation of continuity if many options are given for that. And we know that equation of continuity is satisfied if for a incompressible flow if the gradient of velocity is equal to 0 and the gradient of velocity in here is in fact given. Let me see if I am able to write that down. Okay, should be equal to, yeah, dou u by dou x plus yeah, it'll be dou v by dou y plus dou w by dou z should be equal to 0. And this is the equation of or equation of continuity for an incompressible flow. Let me just also keep the term steady flow. Therefore, we just need to find out what these three terms are, and let's just take the example dou u by dou x. In the question, u is given as by square. Therefore, dou u by dou x refers to dou by dou x of b times y square. Oh, I think I have to script over here. Yeah, it will be by square, and the differential of this with respect to x will be in fact 0. Similarly, it will be dou v by dou y should be equal to very similarly as shown here. It will be dou v by dou y will be the differential of dou by dou x of dou by dou y of ax square, which is in fact again 0. And again, if we consider dou w by dou z, there is no term in the differential for the there is no term in z to be differentiated There's no term in W to be differentiated by Z. So we'll get C times x square y square by d dou Z. It's again 0. Therefore, we can say that we just go back to the question. I think I may have written it down. U equal to and we are constants. By square. Oh, I see. Yeah, so it doesn't matter what value of A you have chosen. So, yeah, the correct answer would be this one. Any values of it doesn't have to be dependent on any dependence between A and B cannot be established here. So this is the correct answer. Next question, given the compressible velocity, steady incompressible velocity distribution U is equal to by square, V is equal to x square, and W equal to cx square y square. The convective acceleration in the x direction is given by what? Yeah, we know that the convective acceleration from the Navier-Stokes equation is given by given as follows. Just take a minute to write that down. It is in fact denoted by ax, which is given as follows. First is the unsteady term. Next is the something known as the substantial derivative or the total derivative as given here will be given by dou times dou u by u times dou u by dou x plus v times dou u by dou y plus w times dou u by dou z. This is the acceleration term in the Navier-Stokes equation, and this together is known as the convective acceleration term. So if u is equal to a times it's y square, I guess. Yeah, a times y square. Then we know that dou u by dou x equal to 0. Dou u by dou x will be equal to 0. Dou u by dou y should be equal to 2ay, 2ay. And similarly, dou u by dou z should be equal to 0. Therefore, and there is no time derivative, therefore we can just safely assume that dou u by dou t should be equal to 0. So from here we need to understand that ax is in fact given, although it's given like this, it will reduce just to u v times dou v by dou y, and we know that v is given here as ax square. So this is a times, just 1 second, yeah. So this is a times, the u is given by ax square, so we'll have to write that down, ax square, and dou u by dou y is given by 2, this is bx square, I guess. and dou u by dou y is given by 2ay. Therefore, the convective acceleration term will come to 2ab x square y. And this is the correct answer, 2ab x square y. Okay, we'll move on to the next question. A frictionless, incompressible, steady flow fluid is given and generated by this equation where u is given by by square, v is ax square, and w is cx square y square. A, b, and c are constants and neglect gravity. We have to find the pressure gradient in the x direction, and for that we need to make use of the momentum balance equation. We have done this we have done questions of this sort in the previous several lectures. Yeah, so this is one of the last week's class where I had taken out this equation over here, and this is in the cylindrical coordinates, but we need it in the Cartesian coordinates, so we'll rewrite it as we do it. So we need to find out the pressure gradient in the, this is given as the y direction. So let us take the y momentum balance and solve it. We know that the Navier-Stokes equation in the y-axis is given as follows, where it is first it starts with the unsteady term, dou, it will be dou v by dou t plus u times dou v by dou x plus v times dou v by dou y plus w times dou v by dou z Now this should be equated to minus del dot p or minus dou p by dou y. There is also a density term that is associated with here, so we have to incorporate that, minus 1 by it will be a minus 1 by rho over here. Now we also have the viscous term, which is in fact given by mu into del dot del u, and yeah, we'll have to incorporate that as well and check what happens. Oh, sorry. Yeah, it will be mu times here it will come as dou square v by dou x square plus dou square v by dou y square plus dou square c by dou square v by dou z square. Yeah, so this will be the first term of the viscous term, and we'll just have to add the other terms as well. And we'll also have the gravity term as well, but they have asked us to neglect gravity. We'll just incorporate that here, and we'll find out what happens to all the terms. And we know that u is a y square, v is this, and w is this. So we just make a note of that here. We have to find out the pressure gradient in the y direction. Therefore, we need dou v by dou t. Now again, as you can see here, just take this term. Yeah. So this will go to 0. We know that this term goes to 0. U times dou v by dou x. This term exists. V times dou v by dou y. We see that v is not a function of y, so this term goes to 0. W times dou v by dou z. So this term again goes to 0. Minus 1 by rho dou p by dou y, we'll keep it as it is because that's what we need to find out. And when we do the double differential, we'll get dou square u v by dou x square will not go to 0. It will come out to 2a. Dou square v by dou y square goes to 0, and dou square v by dou z square also goes to 0. We've been asked to neglect gravity. So based on this information, we'll write down what balance we get. We'll get b times y square should be multiplied by dou v by dou x will come out to 2ax, should be equal to the pressure gradient term over here, minus 1 by rho dou p by dou y, plus mu times dou square v by dou x square will come to 2a. So yeah, so we'll get that over here. Yeah, this is the question, sorry. Yeah, so we need to also neglect this viscous term as well, as you can see here. Yeah, and we'll get this term to be equal to 0. Therefore, we'll get our final, excuse me about that. Yeah, we'll get dou p by dou y to be equal to 2 times a b, or 2, there will be a row terms over here. 2 rho b x y square. Apparently this option was not given properly in the website, in the SWAYAM website, so I'm not sure what to make of it. So the correct answer is option B, is given by 2 rho abxy square. I think I may have skipped a couple of questions in between. Yeah, I think I just skipped one question over here where you have to ask to find the pressure in the x direction. Now the pressure gradient in the x direction is very similar to the pressure in the y direction. So we'll just may start with that. Instead of v, you have u everywhere, here as well. This doesn't change, but this changes. Similarly, this doesn't change, but this changes. And we have to find out the pressure gradient in the x direction, and this would be dou square u by dou x square, dou square v by dou y square plus dou square u by dou z square. And yeah, we have also been given these terms. Yeah, it's given that it is a frictionless, therefore mu should be equal to 0, so we can neglect this entire term. Yeah, we need to understand from this frictionless that there is no viscosity term associated with this. It is an inviscid flow, and yeah, so from here we can find out the rest of the terms. You know that dou u by dou t should be equal to 0, u times, okay, I will just redo it as we were doing for the other one. Take a later, yeah. We know that there is no unsteady term, and u differential of u is not a function of x. U is a function of y, therefore this term will exist. U is not a function of z. Minus 1 by rho dou p by dou x, we'll keep it as it is because that's what we are trying to find out. Mu will be 0, therefore this whole term will go to 0. And we have to neglect gravity. Therefore, when we try to solve this, very similar to the earlier case, we'll get v, that is ax square, times du by dy, that is 2by, should be equal to minus 1 by rho dou p by dou x, and therefore just rearranging, we'll get 1 by rho dou p or dou p by dou x should be equal to should be equal to 2 rho a b x square times y. That equation is the same as option A over here. So this is the correct answer. Yeah, let me know if you have any questions in solving question number 6 and 7. These are very straightforward questions. Now there is one more question in this with this set of questions, that's frictionless incompressible steady flow field is given by such, and we just have to find the pressure gradient in the z direction. Again, this is very similar to what we have already done for x and y. So we'll just quickly derive the equation in the z direction. Okay, sorry. Yeah, z direction as well. Instead of u, we have w everywhere. So yeah, this will be the momentum balance equation in the z direction. Yeah. And again, as we have done for the other two cases, we have to raise of the unsteady term. U is a function, W is a function of X and Y, therefore the first two terms will remain. But W is not a function of Z, therefore this term will go away. And we have to consider a frictionless term and ignore the gravity effects. So same as we are doing. We know that U is by square, and we have to multiply that with dou W by dou X, which is 2cxy square, and V is ax square, and you have to multiply that with 2cx square times y. Yeah, and that we have to equate it to minus 1 by rho dou p by dou z. Therefore, dou p by dou z, we can write it as from here we can simplify it by taking out c into x square y. Okay, you will get this value to be, in fact, this rearranging, you'll get 2 rho cxy times by cube plus ax cube. This is the pressure gradient in the x direction, but I'm not able to arrive at the solution that's been given here for the pressure gradient in the z direction. I think there is some mistake with what they have given the answer, so let me just get back to you on that. Okay, so we'll move on to the last couple of 2-3 questions for the first week. And now a constant thickness film of viscous fluid moves laminar motion down a plate inclined at an angle theta as shown in figure 4. The velocity profile is given as u is equal to c times y square minus h square minus y by h, and the v and w direction to be equal to 0. Find the constant c in terms of the density rho and mu. So we have velocity in the u direction, but nothing else in any other direction. And let's just find out how we can take this equation and solve it. So what we can do is that we know that dou u by dou y exists, so we just need to take the vertical momentum balance or the y momentum balance that we have seen before. And it can be represented as this one that I have said over here. Oh, sorry about that. Yeah, which is this one dou v by dou t plus u into dou v by dou x, etc., etc. This would be in the y direction, the gravity component in the y direction. And as per our figure, if we have to draw an axis, it will be in oh, sorry, yeah. We'll have to draw the axis like so, where we have to say that this is the x component and this is the y component. So if G is acting downwards in this direction with for if this is the direction of gravity, then the component of gravity in the y component in will be in this direction, and it is given that this angle is theta. Therefore, yeah, this angle uh, will not in this angle will be in fact theta. Yeah, so yeah, this will be in fact theta. So this component of gravity acting in the y direction will in fact be g times sine theta. So we have a gravity term. We have a, since it is given that is a viscous liquid, we cannot neglect the viscosity in this direction. But yeah, let's just take what all terms will go to zero here, and we know that there is no unsteady term, and u is equal to zero. Uh, Sorry, u is not equal to zero. I'm sorry about that. Let me redo it from the first. Yeah, so as I was saying, there is no unsteady term, and u is not equal to 0, but v is equal to 0. Therefore, just, yeah, v is equal to 0, w equal to 0. Therefore, all of these terms will in fact go to 0. Here also all the terms will in fact go to 0. Therefore, let us take now the x momentum balance and try to solve it. We know that, yeah, I think I have made a mistake here. So this is not theta. This won't be theta. This will be theta. Therefore, the component of gravity acting in the y direction is actually g cos theta, and the component of gravity acting in the x direction is actually the g sine theta. Yeah, so bad at drawing with a mouse, so you'll have to excuse me for that. So let us take the momentum balance in the x direction as we have said before. Yeah, as this one. And yeah, so this is again gx, not gz. So let us take now what all needs to be cancelled. We'll just take away the unsteady term. We know that u is not a function of x, v is equal to 0, w is equal to 0, so these three terms will go away. The pressure gradient will remain as it is. Let me just see. So yeah, we have to neglect the pressure gradient since the flow is just due to gravity. So we can neglect the pressure gradient over here, and dou square u by dou x square, since u is not a function of x, will go to 0, and dou square u by dou z square, u is not a function of z, again will go to 0. So we just have to equate these two terms, and what we need to understand here is that the gravity term in the x direction is in fact minus g sine theta, where theta is the angle at which it's inclined. Okay, and we know that u is equal to some, yeah, is given as like this, where it is equal to c times y square by square minus y by h. Therefore, if you are finding out what is dou square u by 2x dou y square, we have to just differentiate this twice. Yeah, let me do that right now. So dou u by dou u by dou y should be equal to c times 2y by h minus y by h, sorry, 1 by h, since differential of y is 1. Therefore, if we differentiate it again, we'll get 1 second. Yeah, dou square u by dou y square should be the differential of the term that you're seeing here. Should be equal to c times 2 by h, or to be 2c by h. Now, we just have to substitute for dou square y by dou y square over there. We'll get that as 2 times c times mu, as you can see here, mu by h should be equal to g times sine theta. And if you just rearrange it, we'll get c as yeah, oh sorry, this is actually in the positive direction, since it is flowing with the g is with the flow. So we'll get this as minus g sine theta. Just by substituting, just by rearranging, we'll get this as minus gh sine theta by mu. Yeah, there is one h square over here. That h square will remain as it is. Sorry about that again. So this h square will come back, minus h square g sine theta by mu. Yeah, there is 1 by rho term over here. I forgot about that. I was thinking where that term was coming from, but yeah, it's sorry about that. Yeah, this 1 by rho term will go with g. This will be here, and therefore you'll get yeah, rho gh square sine theta by mu. So therefore the correct answer is this one. Again, if you have any questions, please feel free to reach out to me. I'll be happy to help. Yeah. We have actually two more questions from the week 1 assignments. We have, I think I have completed everything. I hope I have not missed out on anything. Yeah. Consider the incompressible flow field with the velocity components u is equal to 2y, v is equal to 8x, and w equal to 0. Does this satisfy the Navier-Stokes equation? We just have to put it back into the equation. You'll find that this will be satisfying the Navier-Stokes equation. Again, another question that is very similar that was given in the solved assignments is the flow field is just different. So we'll just try to solve this as quickly as possible. So yeah. Same question, just a different flow field. Yeah, so we don't have to worry about the y momentum balance now. We just have to worry about the x momentum balance, and everything else remains the same. Viscous fluid moving at an angle, moving and down a plate at inclined at an angle of theta. And yeah, everything else is remaining the same except that the flow field is now c times y times 2h minus y, and we just substitute that value over here. So dou u by dou y will be c times 2hy minus y square. That means c times this value will change. It will be c times 2h minus, excuse me, yeah, it will be c times 2h minus 2y, because differential of y square will come out to be y. And so the double differential of this will be in fact coming out to 2 times c, or minus 2c in fact. Therefore we can just replace this value as minus 2 times c, where dou square u by dou y square is minus 2 times c, and we have to multiply that with mu and not mu by h, and equate that to minus 1 by rho g times sine theta, as we have done earlier. Finally, upon rearranging, we'll get the final value as minus rho times g sine theta by 2 mu. Yeah. Rho, this negative sign both sides will cancel away, so it will be rho g sine theta by 2 mu. One second, let me just see. Yeah, it will be rho g sine theta by 2 mu. Okay, I think we are done for the week 1 assignments. Let's just go through what was taught in week 3, which is in fact questions on circular Poiseuille flow, Taylor-Couette flow, viscosity measurements, and types of fluids. So let's just do one question based on that and stop for today. So we know that the week 3 we'll do a problem on these kind of questions which were discussed in class. So let's now start with this. Consider the steady incompressible parallel laminar flow of a viscous falling fluid between two infinite vertical walls as shown in figure. The distance between the walls is h and gravity acts in the negative z direction. There is no applied force or pressure driving the flow, and fluid falls by gravity alone. The pressure is constant everywhere in the flow field, and calculate the velocity field and sketch the velocity profile using appropriate non-dimensionalized variables. generate an expression for volumetric flow rate per unit width as a function of R, M, H, and G. Calculate the volumetric flow rate for an oil, volumetric flow rate per unit width for an oil film of 5 millimeter with density 888 kilogram per meter cube and viscosity 0.8 kilogram per meter second. So it's just a very simple equation where we need to take out the y momentum balance, and just it's very straightforward whatever we have done here. Let us take the it's in the x and z direction, so we just take the z momentum balance, or whatever it is, and we know that there is only gravity term that's acting, and there is no other term. We just have to find out u as a function of z. So yeah, there is if we just have to find out u as a function of z over here. Oh, sorry, we just have to find the function of w as a function of z. Since there is flow in the negative z direction, we have to take the z momentum balance. Flow, let's just make that. No, flow is in z direction. Therefore, w is a function of x and nothing else. Yeah, so we just take the our z momentum balance as we had done earlier over here. Yeah, and write that down over here. We have to assume a few things as we have been doing it for some time. Assuming steady state, and u is equal to 0, v is equal to 0, and w is only a function of z, and it is given that in the question it is given that there is no applied pressure driving the flow, and the fluid falls by gravity alone. Therefore, we can neglect minus 1 by rho dou p by dou z. We know that w is a function of x, so we'll have to keep this. W is not a function of y or z. And the gravity term will in fact remain. So while we have all of this, let us now try to understand what all we have done. So w is a function of z, and we have made sure of that. Yeah, and gz will be the gravity acting in the negative direction, so it will be minus g. Yeah. Now we just have to substitute the values. Mu into dou square w by dou x square. Okay, yeah, mu into dou square y w by dou x square should be equal to minus g. Therefore, yeah, dou w by dou x, if I integrate this once, I'll be able to get dou w by dou x, which is equal to minus minus g, oh sorry, here we go, minus g by mu minus g by mu. I have to integrate it once, so I'll get an x plus c1. Let this be the constant of integration. We'll get this as c1. Now if I integrate this again, I'll get w is equal to, let me put it in a equation over here. Yeah, we'll get W is equal to minus G by mu times X into, this will again be X squared by 2 plus, oh, okay, 1 second, let me just make a better way. Yeah, minus G by mu X squared by 2 plus C1 into X plus C2. Yeah, now we have an equation for W in terms of X. We just need to understand the boundary condition. We know that at the two volts where H is plus or minus, X is plus or minus H by 2, there is a no slip condition. So we can write that X is equal to plus H by 2 and X equal to minus H by 2. We have the conditions at W equal to 0. And the second, so let this be boundary condition number 1. Yeah. And boundary condition number 2 is that at X equal to 0, we'll have to get the maximum velocity, or there will be zero shear stress at the center, and that will be equal to dW by dx should be equal to 0. Substituting these values, if you substitute the the second one, we'll get C1 to be equal to 0, and we'll get the final expression for C2 from here, from the second, from the first relation, where you'll get, yeah, once again, yeah, you'll get dW is equal to 0 over here. So yeah, let's just put that for H square by 4. C2 should be equal to it'll be, here it will be H square and here it will be 4. So we just need to resubstitute this into the equation. We'll get W is equal to, yeah, I'll write the equation in the equation box. You get W is equal to rho times G again. I keep forgetting there is a density term that is there as well. I think I have not included anywhere. There is a 1 by rho term over here. Rho G set, sorry, this is not 1 by 2, this is in fact rho G set. Yeah. So there should be a rho term over here, here, and rho G mu into rho G by mu into H square by 4. So therefore W should be equal to rho times G by 2 G by 2 times mu uh, yeah, times x square minus h square by 2. Yeah, you'll get this as the velocity profile over here. And we see that it is a parabolic profile with respect to x. We just need to non-dimensionalize it now. So we can write W star as W times mu by, or you can divide this with that, W times, one second, yeah. Yeah, so we can define W star, which is the non-dimensionalized velocity, as mu by rho gh square, and we can define non-dimensional length scale x star as x by h. Therefore, we'll get then the non-dimensionalized term, we'll get W star from here as we'll get it as there won't be any rho or g, it will be just part of the system. It will be 1 by 2 times x star squared. Yeah, 1 by x star square minus 1 by 4. Yeah, so this will be the non-dimensionalized profile. There will be another one. Sorry, W star should be, W star should be equal to 1 by 2 times x star square minus 1 by 4. Yeah, so for finding out the volumetric flow rate per unit width, we just have to integrate this. I think I leave that as a homework. If you have any doubts, please let me know. So volumetric flow rate per unit width can be found out Q by L, as we call it. It can be found out just by integrating this with respect to dx. So integrating the function w with respect to the dx, and we just have to integrate within the limits of minus h by 2 to h by 2. And I'll just give you the answer right here. Please confirm it once you're getting to know what the values are. You'll get this as minus rho g times h cube by 12 mu. So I'm just asking you to do this as homework. Prove this. So I think we can stop here for today. If you have any more questions, please feel free to ask in the forum on the Swayam website, where you can ask a ask a question over here, and I'll be happy to respond. If you have any more questions, again, please come to the class and I can feel free to ask me. If you have further questions, feel free. I'll be as happy to respond to you. I sincerely thank you for your time and attention, and I hope you have a great week ahead. Happy learning. Thank you.